Yo, 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 welcome to Physics with Vinay. Now let's talk about oblique projectile. So oblique is basically a projectile is thrown from a height above the ground level. Let's say that height is h. It will land somewhere on the ground. So I'm going to say this is the horizontal displacement is my range. Let's say it's projected at an angle theta and a speed u. So the question can ask you to find the time taken, they can ask you to find the range, they can ask you to find the angle of striking the ground. So let's just quickly look at the equations that you can use here. So if I take my x-axis to the right and y-axis upwards, this is my choice. You can take y-axis downward positive as well. That's your choice. So let me just write down first for the equation. I know that the displacement has a y component of minus h. This is the displacement vector. So it has a y component of minus h because I have taken upward as positive. So positive y-axis. So I'm going to write displacement in y component is equal to uyt plus half ayt squared. So sy would be minus h, uy would be u sine theta times t. And what about acceleration? The acceleration is g downwards, so it will be minus g. So this is how you will get your time of flight. So this is the way that it's usually done in order to get the time of flight. However, let me just show you a faster method where you don't actually have to solve this quadratic equation anymore. See, if I just denote this velocity by v, I know vy is equal to uy plus ayt, and therefore I can write my time of flight as vy minus uy divided by ay. So what is vy? We know vy using the third equation. So can I write vy as simply uy square plus 2gh with a negative sign because vy will be downwards. I have taken upward as positive y-axis minus uy divided by. So this will simply be uy is u square sine square theta plus 2gh plus u sine theta, uy is u sine theta divided by g. So that is your time of flight. So I hope you've understood how we don't actually have to solve the quadratic equation in order to get the time of flight in an oblique projectile. We've just used the first equation, and in Vy we've substituted the third equation. So it's slightly faster, whatever you're comfortable with, but I personally prefer this method that I've shown you here without actually resorting to solving a quadratic. Alright, now what about range? If I know the time of flight, can I get the range? Yes, I can get the range as simply the x component of velocity u cos theta multiplied by the time of flight because there is no acceleration in the x direction. Alright, what about this value of v? We already saw that v is u square plus 2gh. You can get it by the third equation or energy conservation. And what about this angle phi? I'll just equate the x components of velocity. So I'll have v cos phi is equal to u cos theta because once again there is no acceleration in the horizontal direction. And this is how you can get all these parameters. Now a very interesting result about this horizontal range is what is its maximum value and at what angle does it occur. We know in ground to ground projectile the maximum range occurs at an angle of projection of 45 degrees, and we know how to calculate that maximum range. But what about this oblique projectile? So there's a very cute result for the range which you can remember, and it will be very helpful in a certain type of problems that we'll look at later on in this lecture. So first let me just go to the next slide. I'll show you the value for that maximum range, and then we'll prove it as well, and then we'll look at its applications. So if I say the initial speed is a constant, but let's say this theta is a variable. So you can choose whatever theta you want, and I want to choose such a theta which will maximize my range on the ground. The horizontal displacement, I want to maximize it. So the maximum horizontal displacement comes out to be equal to, let's say the speed on striking the ground is v, uv by g. Initial speed multiplied by the final speed divided by g. I would suggest that you remember this. It's pretty easy to remember, and a certain type of problems become very easy to solve using this expression. Now let's just quickly prove this also. It's not a difficult proof. So basically I want to find the maximum value of r, and I can throw the particle at any angle but with the constant speed. So theta is a variable here, and of course the height is also known to us, and in the process we'll calculate the initial angle of projection as well. And now we are left with a very simple expression for the range. So this is actually a very neat expression for range, uv sine phi by g, where phi is, remember, the angle between the initial velocity vector and final velocity vector. Okay, now it should be very obvious. If range is maximum, what will be the value of phi? 90 degrees, and that's it. Therefore my range maximum value would be uv by g. And we also know that this will occur when the angle between the initial and final velocity vector is 90 degrees. So occurs when u vector is perpendicular to v vector. So that's just another neat result that we've derived here. Now let's look at the angle at which the particle should be projected in order to maximize this range. So we got that the initial velocity and the final velocity when it's striking the ground are perpendicular to each other. That is what we got. So let's say this angle is theta. So clearly this angle would be 90 minus theta, because v and u vector are perpendicular to each other. Now I can just equate the horizontal components of velocity, because here there is no acceleration in the horizontal direction. So can I write u cos theta is equal to v cos of 90 minus theta, and therefore I have u cos theta is equal to v sin theta, and therefore tan theta is equal to u by v. And we already know the final speed because we know the height. I can always write my final speed as u squared plus 2gh. So basically tan theta is u by v is the initial angle of projection such that the horizontal range is maximized. Alright, so this is another Pathfinder question that we have here. Looks a little difficult, but it's absolutely straightforward once you've understood whatever we've studied so far. So I have water flows out in all directions with the same speed from a sprinkler consisting of a perforated spherical shell fixed at the end of a hose. So basically there is a shell that is emitting water in all directions. When the sprinkler is fixed at the ground, the maximum height attained by a water stream is h. If the sprinkler is shifted to a height h above the ground, by what factor will the watered area on the ground change? So let's take a look at first what kind of a diagram we can draw for this question. And if you want, you can stop the video and try it out on your own. Okay, so first of all, when the sprinkler is on the ground level, it is ejecting water in all directions, including the vertical directions. So the water trajectories will be parabolic except one of them, which will be vertical, which is going straight up. So that trajectory will have, the vertical trajectory will have the maximum possible height. And how much will that be? The final velocity at the highest point will be 0. So I can simply write v squared is u square minus 2gh. I know v is 0. So the initial speed would be equal to 2gh, root of 2gh. Right? So this is one relation that we are going to use. Now the sprinkler is shifted to a height h above the ground level. And once again you have water being ejected out in all directions with the same speed u as mentioned in the question. The question asking find the area on the ground that will be watered by the sprinkler. So basically you should be able to see that because it's in all directions, there will be a circular region, and the radius of that circle will be the maximum possible range of this oblique projectile. Now we already found out that maximum possible range was equal to uv by g. So we know the value of u, I can get the value of v, and once I get the maximum range, I can even get the radius, and therefore I can get the area. So if you want, you can once again pause the video right now and proceed forward with this and get the final answer. Alright, so I'll just do the final calculations. I have the maximum range, which is the radius of the circle, which will be uv by g. So this radius would come out to be u is root 2 gh, and v would be u squared plus 2 gh. So divided by g. So I'm going to substitute this u squared as 2 gh. So this will come out to be root 8h, and therefore the area that is watered would be pi times this radius squared. So that will be 8 pi h squared. So this is the area that is watered when the sprinkler is at a height h. The original watered area was very simple because it's simply a ground to ground projectile, and we know the maximum range will occur at 45 degrees. So once again you will have a circular region which is getting watered, and the radius of this will again be the maximum range. So the maximum range for a ground to ground projectile would be u square sine 2 theta, so that will be sine 90 degree by g. So that will be u squared by g, and u squared is nothing but 2 gh, that will be 2h. And therefore the area watered would be pi into 2h the whole squared, which would be 4 pi h squared. Alright, so now we need to take the ratio. So we already found out that when the sprinkler was at a height h, the area watered was 8 pi h squared, and when the sprinkler is on the ground, we calculated the area to be 4 pi h squared, and therefore the ratio is 2:1. So that's my answer. So I hope you've understood how easily we were able to solve this question, provided we know the fact that the maximum range is uv by g. So once you know that result, these type of questions become extremely easy. A horizontal electric wire is stretched at a height h equal to 10 meters above the ground. A boy standing on the ground can throw a stone at speed 20 meters per second. Find the maximum horizontal distance x at which a bird sitting on the wire can be hit by the stone. Alright, so this question is only for theoretical purposes. Please do not try this demonstration in real life. So this is like an oblique projectile. And like an oblique projectile, we already found the maximum range during our lecture. We know that formula. So that formula for the maximum range during our theory lecture we discussed this was uv by g. We use the initial speed, v is the final speed, and g is the, of course, the acceleration due to gravity. And therefore in this situation the initial speed would be 20 given to us. What will be the final speed? We know the height h is 10 meters. So I can write down the final speed as u squared minus 2 gh when the stone hits the bird. So that will be 400 minus, so root 200, so 10 root 2. So this will be 10 root 2 divided by 10. So this will be 20 root 2 meters. And that's it. So there's no need to use the equation of trajectory. That's the standard way. You use the equation of trajectory, then you differentiate it to maximize it, or you express it in terms of a quadratic in tan theta. And anyway, this is the shortest method. You will find less than a minute to solve this question. I hope you've understood this.